Welcome back, everybody. I think we're going to begin the afternoon session, but before I begin, I think everybody knows about the reception tonight, right? Or this evening, that is. It's going to be in the lobby. But before that, we'd like to have a group picture just outside. So after this session ends, if you agree, you have to give us permission. We'll go outside. We'll go outside on the stairs here and take a group picture and then move on to the reception. This session is, what is the session title? I don't even know. There's many forms of resonances, and I think it's very sort of quite fitting. Let me begin with this paper of I don't know how we got this. This paper of Fano, which appeared in 1961, Effects of Configuration Interaction on Intensities and Phase Shifts in Physical Review, which was an extension of his previous paper in University in 1935. I don't know where it stands in relation to other papers, great papers in physics, but it's been cited a little bit over 4,000 times already. And in the last 6 months of 2002, more than 80 times. So there is. Lost the mic. Is it okay now?
I think it.
So as a testament to the longevity of this work, it's sort of a classic work in physics, where Fano actually concentrated on describing the autoionization in atoms as mixing of a discrete state with a bunch of continuum electronic series, which is essentially can be written down mathematically like this, where the first term is the discrete wave function, and then you have an integral over the continuum states. Was first pointed out by O.K. Rice in the first issue of JCP. In 1935 paper, Fano discretized the continuum. I think it's something that is actually well known to the practitioners of R matrix today on how to do. But in the 1961 paper, he added an imaginary term to this coefficient in this two by two Hamiltonian, which comes from essentially the collision theory. And he calculated or derived the coefficient for in front of the discrete wave function as such, which has effectively almost like a Lorentzian profile, except that it has a shift here, f, as a function of energy, and gamma is, which the width is a function of energy as well. And eventually, to make the story short, he was able to derive this expression, which is now pretty well known, for any type of intensity or cross-section as being Q plus epsilon, where epsilon is some sort of a dimensionless energy parameter, plus Q, which is now known as the Fano parameter, squared divided by 1 plus epsilon squared, where Q is written as such, where T is your favorite transition matrix element. And I is the initial state, which couples to this supposed to be the continuum state, phi sub E, and the numerator is the initial state transition matrix element to a dressed, discrete state. So the discrete state is not the ordinary discrete state, but one that has been dressed by the continuum. So, or in his language, has been diluted by the continuum. So when Q, for instance, in other words, when the numerator becomes 0, then you get essentially what people term window resonances. And when Q becomes infinite, in other words, the coupling to the continuum goes to 0, becomes the usual Lorentzian resonance that we all know. The extension to overlapping resonances with several continua was made by Fred Mies a few years later, who is actually now in the audience. The famous experiment, of synchrotron experiment done by Madden and Codling, in 1963 effectively showed these type of resonance behavior in atomic physics, where these asymmetric profiles were seen, and in a back-to-back paper by Fano himself and Pratt and Cooper was described as sort of like mixing of two configurations, the 2s and 2p. These are resonances below helium plus n equal to 2, which stands today, even as we speak, as the language, the plus-minus states in atomic resonances. Here's one example of experiment done by Nora Burra and calculations, I think, by Tom Gorsico, the two of the speakers in this session, of an experiment on argon, where they saw resonances belonging to these thresholds. Actually, when I say thresholds, here you have the fine structure thresholds, and you see these asymmetric profiles. I want to finish as quickly as I possibly can. The issue here is that the nature gives us these resonances, and of course Fano was able to describe them. It is also possible to control the quantum interference, and this is something, an aspect of which can appear in quantum optics. And the speaker, one of the speakers today, Steve Harris, has done this really breakthrough experiment in the early 90s, where he introduced the control or a coupling laser to couple to a state. This is like a three-level system, so you have interferences that occur because of this coupling between the states 2 and 3 and 1 and 2 lead to a destructive pattern, a so-called darkest state, that will make a material transparent to light. And the experiment he did was on autoionizing states in strontium, and these are levels 1, which is the 5s5p in strontium, 2 in this cartoon is the 4d5p, and 3 is the 4s5d, doubly excited state. No, that's not a double. I'm sorry, this is a 4d5d. That's a doubly excited state. It's not 4s. It's 4d5d. And what he was able to show that you could actually reduce the absorption to practically to 0. Something similar to this. So the transmission essentially peaks in a window, so-called EIT window, electromagnetically induced transparency window, goes way up. This is not from the experiment of Steve Harris, but he got something very close to this. This is actually from the experiment of Lini Hao, and effectively this idea is the engine behind the so-called slow light experiments that I'm sure you've all heard and read about. This is from Lini Hao's experiment, where the index of refraction shows this asymmetric profile and effectively rises very quickly through this window, so you could actually stop light. Another way of looking at interferences is going to be discussed is in mesoscopic systems, or in condensed matter, is going to be discussed by Bill Gadzuk, Ned Wingrain, and Mark Kastner. This is an experiment and theory done, Ned Wingrain, who's going to speak today, on using the STM tip measurement of differential conductance on I believe it's a gold, he can correct me, gold surface, 111 surface, by installing, absorbing a cobalt atom here and not having a cobalt atom. When the cobalt atom is absorbed, then the differential conductance shows this asymmetric profile. And effectively, the way to see this is to imagine that, for instance, the electrons from the STM tip can go into the discrete states in the cobalt atom, and you also have the essentially the conduction band electronic states in the solid material, which can interfere as a continuum, giving rise to this interference pattern. There's also the so-called designer atoms. Depending upon your taste, you could call them quantum dots or single electron transistors. And Mark Kastner is going to describe it, I'm sure, in great detail. Essentially, electrons confined to small regions of space that interact by tunneling to source and drain leads. Here's in a schematic how these things could actually look like. So here are the leads on the left and the right, and here's the confined area, which are coupled. The states in here, the quantized states, can actually couple to the electronic states on both sides. By tuning the voltage, a lot of control can be exercised over these systems. So that's why they're called artificial or designer atoms. And here's an example of how you could, by turning the coupling between the left and right leads, you could actually go from a quantized electronic states in here to so-called Kondo regime, and then later on to the Fano regime, where you see the asymmetric profiles of the conductance. So this is going to be, I think, part of the talk of Mark Kastner. Just very recently, a very clever experiment, at least in my view, was done in Japan, where they did a twist on this Aronoff-Bohm interferometer, where what they did was to take, you got a magnetic field here, and then in one arm they had essentially nothing, and on the other arm they put a quantum dot, and what they saw were beautiful interference patterns effectively coming from the interference through this quantized conductance through the quantum dot and continuum transport through the other arm, obtaining this interference picture. So with that, I'll yield the floor to Bill Gadzuk, who is going to describe some of these things. It's the Fano resonances in condensed matter physics, I think the title of his talk. So I'm going to give you 30 minutes and 5 minutes.